This is a problem on stresses in a ball thrust bearing. The problem is a ball thrust bearing with 7 balls is loaded axially across its races through the balls. The question: what is the size of the constant patch on a race? What are the stresses developed in balls and races? What is the depth of the maximum shear stress in a ball? And the given data, number of balls are 7 balls, so 7. Diameter of each ball, that is 10 mm, but we have to solve this problem in terms of imperial system, so we will convert it in terms of inch. So that is 1 inch is 25.4 millimeter. For 10 mm, that will be 0.394 inch. And next axial load is 151 lb, that is 151 pounds. That will be for 7 balls, and for each ball, one ball, it will be 21.5 lb per ball. Okay. So next given condition or assumption is, given assumption it is the 7 balls share the loads equally, the rotational speed is sufficiently slow, and therefore we will consider this as a static loading problem. Let us start with the solution part. Initially, a geometric constant, that is b is equal to 1 by 2 1 by r1 plus 1 by r2. So here r is the radius of balls. Radius of ball, that is diameter is 0.394 inches, so therefore 0.394 by 2 is the radius. Okay, so r2 is not mentioned, that's why it is infinite. So we will get the value of b, and that is b is equal to 2.54. Next is material constant, that is m1 is equal to m2 is equal to 1 minus Poisson's ratio square divided by E1, that is Young's modulus. That is Young's modulus we will be considering as 3 into 10 to the power 7. So answer is 3.072 into 10 to the power minus 8. Next is half width radius of the contact patch, that is A is equal to cube root of 3 by 8 into m1 plus m2 by b into f. Here contact patch means the balls or races making contact with the raceway. This is raceway, and consider this as a ball. This is making contact. The portion of the ball making contact on the raceway, that is contact patch. Okay, this will be the contact patch. This portion is contact patch. So A is equal to, substitute here, there is m1 and m2, so they are equal. So m1 and m2 we have calculated before, so they are same value, so I have multiplied by 2 into 3.072 into 10 to the power minus 8. So this is the one. And b and f value is 21.5 lb, so we'll get 0.00858, that is equal to 0.0058 inches. See, while calculating you'll get fractions, isn't it? So don't make it full number. If you want, write 5 7 something, whatever number, but I have written here full. Okay, because during calculation, if you consider a short fraction, then it may vary your answers. So circular contact patch area is equal to pi a square, is 1.057 into 10 to the power minus 4 inch square. So average and maximum contact pressure, P average F by area, and P max, that is 3 by 2 into P average. So next, maximum normal stresses in the center of the contact patch at the surface, that is sigma z max is equal to minus P max, that is minus 305,381 pounds per square inches. Sigma x max equal to sigma y max is equal to minus 1 plus 2 Poisson's ratio divided by 2. Next is depth of the maximum shear stress in a ball. tau yz max is equal to p max divided by 1 minus 2 Poisson's ratio by 2 plus 2 by 9 into 1 plus Poisson's ratio, same here also Poisson's ratio. So substitute and you will get 103083 psi. Next is z at tau max. A is equal to square root of 2 plus 2 Poisson's ratio divided by 7 minus 2 Poisson's ratio. So we'll get 0.0037 inches. So shear stress at the edge of the contact patch at the surface. This is the equation, and tau xy is equal to 44,789 psi. So this is the solution.